Hey students, today I'm going to record a video called Significant Figures. Now, if you're going to take science in college or if you're taking upper level science courses in your high school, you're going to need to know how to use significant figures and how to become very comfortable with them. At first, it's a little bit strange, but once you get used to using significant figures, it just becomes second nature. So the goal of this video is to help you understand how to use significant figures and to give you some practice to hopefully help it become second nature for you too. I got these notes from a wonderful teacher by the name of Mrs. Verkler. She's retired now. And I got some of the samples from Pearson Chemistry, the Foundations edition. But these rules are cohesive all the way through an AP chemistry course you may or may not be taking. Now, what does significant figure mean? It means that all the digits in a measurement are known with certainty plus one estimated digit. So what do I mean by that? For example, if I have the measurement 14.7 centimeters, that means that in this number, the 1 and the 4 are known with certainty, and the 7 is an uncertain digit, or an estimated digit. So in any measurement or number in science, that's how we view the number. It has a certain number of certain digits and then one estimated digit. And that estimated digit is going to be our last digit. You can only have one estimated digit. Significant figures also give us an indication of how sensitive a measuring instrument is. You can only estimate one digit, so the more decimal places you have in your answer, the more sensitive the measuring instrument that you're using is. For example, if you're using a thermometer and the temperature falls between 22 degrees Celsius and 23 degrees Celsius, and you estimate the reading to be 22.9, you have 3 digits in your answer. So here's your 22.9. These two numbers would be certain, and then the 9 would be your estimated digit. So what would that mean about the sensitivity of your thermometer? That would mean that if you had the thermometer, it would probably only have a marking for 22 and a marking for 23. And if your mercury, well, it's not going to be mercury anymore, alcohol stops right before the 23, you could estimate it to be 22.9. But you couldn't estimate that to be 22.85. Why? Because that would mean that these two numbers would both be estimated, and in any measurement you can only have one estimated number. Let's look at these two thermometers. If I ask you to read the temperature off of thermometer A, most of you would probably say, well, if this is 16 and this is 18, then this would be 17. That looks to be a little bit less than halfway. I'm going to say this is 16.4 degrees Celsius. Now, everybody's going to be very certain about the 1 and the 6. But someone else might look at it and think that that is right halfway there, and they may have said it's 16.5. They're not necessarily wrong. Why? Because this number here and this number here are both your estimated digits. Because of the sensitivity of this instrument here, we can only estimate to the 10th place. However, let's look at thermometer B. In thermometer B, we have 16, and then we have these little hatch marks that tell us exactly where 16.1, 16.2, 16.3, 16.4, and 16.5 are. So now we know for sure that this is 16.4. It's a little more than 16.4, about halfway between 16.4 and 5. So we're going to estimate that last number to be a 5. Notice now, because this thermometer has more markings on it, it is a much more sensitive instrument than thermometer A, and we can estimate to the 100th place. Now, someone may have looked at thermometer A and said, no, I could have said 16.45. I know I could have. That's exactly what it looked like to me. but you can't do that. You can only estimate one more past the markings that you're provided. So you're not allowed to estimate 2 places. Let's look at these measurements. Here we have 3 meter sticks. The first meter stick has no markings on it. So when you estimate, you're going to say that's 0.8 meters. The next meter stick has markings of every 10 centimeters. And when you get to the 80, you see that the door ends right before the 80. So you might estimate, okay, the 0.7, it's 0.7 of a meter or 70 centimeters. So let's estimate this in centimeters first of all. It's going to be about 70 centimeters plus a few. It's leaning close to the 80. Let's call this one 77 centimeters, which is 0.77 meters. Now in 77 centimeters, we're certain about this number, and our estimated number is that 7. Now let's look at the last ruler, and I'm going to make this a little bit bigger. In our last ruler, look here. Now we have hatch marks between the 70 and the 80, and so we can go 71, 72, 73, 74, 75, 76, 77, and it's a little bit past the 77, so we could call this 77.2 centimeters. Now our estimated number goes all the way to the 10th place for centimeters or to the 1000th place for meters. So once again, we can only estimate 1 digit past the markings on the instrument that we're using. Now let's consider the accuracy of these devices. We can only be precise as the device that we're using. This one goes in increments of tens. So that means we can only estimate to the ones place. This one here goes in increments of ones. So it goes in increments of ones. That means we can estimate to the 10th place. You can tell if you're measuring and you don't get down at eye level, you're going to come up with the wrong answer, okay? So we're going to get down at eye level with these, and it's hard to do well with a phone, but when I get down to eye level with this, I can see that it's slightly less than 10, so I'm going to estimate this first one to be 9. Then when I get to this one, if I get down to eye level, this one looks like just a little bit above 9. So I'm going to call this one 9.2. So now let's talk about the rules for determining significant figures. Rule number 1 says any non-zero digit is always significant. Okay? So 24.7 has 1, 2, 3 significant digits. 2 of them are certain, the 2 and the 4. 1 of them is uncertain or estimated, the 7. But the total number of significant digits is 3. In the second one, we have 3 significant digits again, the 7, the 4, and the 3. These 2 are certain. This one is estimated, but we still have 3 significant figures, or 3 Sig Figs. And in the last one, we also have 3 Sig Figs. Now notice something here. We did not call this 0 here as significant. Why? Because it's a placeholder, and that rule's coming up. But rule number 1 says non-zero digits are always significant. Rule number 2. Rule number 2 is very obvious. It says that zeros between non-zero digits are always significant. So for example, if I have 4,005, all those numbers are significant. Why? Because I can't throw out the zeros, then I have 45. I guarantee you, if I owed you $4,005 and I said, well, the zeros aren't significant, so I'm just going to give you 45, you'd be very frustrated, and rightly so. So those zeros are there for a purpose, and they are always significant. So zeros inside of a number are definitely significant. So that one has 4 significant figures, 3 certain and 1 uncertain. This one has 1, 2, 3, 4 significant figures, 3 certain and 1 uncertain. And this one here has 1, 2, 3, 4, 5, 6 significant figures, 5 certain and 1 estimated or uncertain. Okay, so we have 2 rules so far. Number 1, non-zero digits are always significant. Number 2, the zeros between the non-zero digits are always significant. And then number 3, we've already hinted at it, is that zeros at the beginning of a measurement are never significant. They merely serve as placeholders, or they draw attention to where the decimal point is. Now, this is why we like scientific notation so much, because when you write in scientific notation, there's no question about are the zeros significant or not, because you don't have zeros in front of a number as a placeholder. Scientific notation gets rid of that. But let's first of all look at these 3 sets of numbers without scientific notation. Here, this first one, 1, 2, 3, those 3 zeros are placeholders. They're telling you that the 7 is in the thousandths place, the 1 is in the 10,000ths place, and you have 0.0071 of a meter. Guess how many significant figures this is? This has 2 Sig Figs, 1 certain and 1 uncertain. This number here, 0.42. The 0 is a placeholder. It's telling us that the 4 is in the 10th place, the 2 is in the 100th place, so there's once again 2 Sig Figs. That 0 in the front is not counted as significant. It is merely a placeholder. And then in the third instant, oh my goodness, look at all of these zeros. This is why we prefer scientific notation. 1, 2, 3, 4, 5. We have 5 zeros, and then we have 9, 9. Guess how many Sig Figs we have again? We have 2 significant figures. All of those zeros are placeholders. So the way to get around this so it doesn't look so bad is to write this in scientific notation. Now when we write in scientific notation in science, hence scientific notation, we always write the number, the decimal, and all the other numbers times 10 to the whatever it is. We always write our number, our decimal, and all the other numbers times 10 to whatever it is. Sometimes students will write this. Now that's not proper scientific notation. Why? Because you always want your number, your decimal, and all your other numbers times 10 to whatever it is. So let's look at these 3 numbers that we just saw. The 0.0071 in scientific notation is going to be 1, 2, 3. 7.1 times 10 to the negative 3. The next one, 0.42, we're just moving our decimal 1 place. 4.2 times 10 to the negative 1. Now please don't memorize if you move it to the right, you make it negative, you move it to the left, you make it positive, because what if they give you something flipped around and then your poor brain is going to jumble it all up and you're going to get it wrong. Remember, tiny numbers have a negative power of 10. Large numbers have a positive power of 10. Tiny numbers, you're going to have numbers that are smaller than 1. You're going to have 10 to the negative something. Large numbers, numbers greater than 1, you're going to have 10 to the positive something. All right, so 0.42 is going to be 4.2 times 10 to the negative 1, and 0.000099, let's see if I can make this bigger because it's getting all jumbled up. Let's see, 1, 2, 3, 4, 5. So that's a tiny number, so it's going to be 9.9 times 10 to the negative 5th meters. Do you see how writing in scientific notation here makes this very clear that we have 2 Sig Figs for all 3 numbers? 2 Sig Figs for all 3 numbers. All right, let's go over our rules again. Rule 1, non-zero digits are always significant. Makes sense. Rule number 2, zeros inside of non-digits are always significant. Non-zero digits are always significant. Rule number 3, zeros at the beginning of a measurement are simply placeholders. Now that leads us to rule number 4. Rule number 4 depends on a decimal point. Because now we're going to have zeros after a number. Are those zeros significant or not? Well, it all depends on the mighty decimal point. So there's a decimal point, there's a decimal point, there's a decimal point. If a decimal point is present, the zeros at the end of the measurement are significant. Now, I'm a Christian, and I always tell my students that they have significance in Christ. You were created for a purpose, and you have significance. So, as a little joke, I put on my door in my classroom a decimal, and then I say, decimal point is there, you are significant. So those zeros are significant if they have a decimal point. So it's a little joke that we have on our door. I also have this on my door. Delta means change in, so I say if you see a sign on a door with a delta on it, that means a scientist is in there change in, so you better not come in. Okay, but back to significant figures. All of these have 4 significant figures. 1, 2, 3, 4. Why? The decimal point makes them significant. This one has 4. 1, 2, 3, 4. Why? The decimal point makes it significant. This one has 4. 1, 2, 3, 4. Why? The decimal point makes it significant. Okay, so rule number 4 says to us, zeros at the end of a measurement are significant if a decimal point is present. So then, part B of that rule would be if there's no decimal point, the ending zeros are not significant. All right, so let's look at these. Here we have 300 meters. Do you see a decimal point here? I don't see a decimal point here. So this is the only significant digit, so this number has 1 significant digit. Let's look at the next number, 7,000. Do you see a decimal point here? I don't see a decimal point here. So therefore, the only significant digit is this 7. So this number has 1 significant figure. And then this last one, 27,210 meters. Do you see a decimal point here? I don't see a decimal point there. So therefore, this number has 1, 2, 3, 4 significant digits. We cannot count that 5th one as significant because there is no decimal point. All right, sometimes you have a number like 300 and you want those zeros to be significant. Well, you can put this awkward decimal sitting right there like that, but people are like, is there a dot there? Did they mean to put that? Is that just a mark on the paper? What's the way around it? Our good friend scientific notation, 3.00 times 10 to the 2. That means I have 1, 2, 3 significant digits. So now what we're going to do is we're going to practice some. So let's practice based on the 4 rules of significant digits that we've learned. Okay, your job is to tell me how many significant digits are in each one. So pause the video, write the answers, and then come back. Okay, hopefully you did that. In this one we have 1, 2, 3. 3 significant digits, no zero, so we don't have to worry. In this one, we have a 0 in the middle, but it's part of this number, so there are 3 significant digits. In this one, we're ending with zeros, but I don't see a decimal, so the only significant digit here is the 7, and that's a 1 significant digit. And in the last one, we have this awkward decimal sitting right here, which tells us that these are significant, so we have 3 significant digits. This one, to write this much better, would be much better written in scientific notation. Now we're for sure there's 3 significant digits. We're not sitting there wondering, is that decimal meant to be there or did someone just make a mark on the paper? Okay? All right, now let's look at numbers 5, 6, and 7. Stop the video. Okay, so when we look at this one, this 0 here is a placeholder. Oh, there is a decimal, so if I see any zeros later on, I don't, but if I did, it would be significant, so this has 3 significant digits. Here we have a 0 as a placeholder, here we have a 0 at the end, but we have a decimal, so therefore that 0 at the end is significant, so there's 3 significant digits. Here we have a 0 as a placeholder. We have a decimal. That means that these zeros are significant, so we have 1, 2, 3 significant digits. Okay, if you got all 7 of those correct, let's move on to some more practice problems. If you did not get them correct, go back and then listen to the rules again. All right, now I want you to stop your video and I want you to write down how many significant digits there are in each of the following numbers. Okay, when you did this one, you should have said 1. These zeros are between non-zero digits, so this one has 7 significant digits. This one has this awkward decimal sitting here. It looks like it's meant to be there, so all these numbers are significant, 7 significant digits. This number here has been rewritten in scientific notation, which now shows you 100% that all those zeros are significant, so this one has 7 significant digits. Here's something. What if number 2 had been written like this, and you know, according to the measurement instrument, that only these 3 zeros right here were significant? How would you write that in scientific notation to show that it had 3 zeros that are significant, 3 that aren't, and it's 3 million? Well, you would write it in scientific notation, except you would only include 3 zeros in the number. So now we have 3 million with 3 of those zeros being significant. See the difference between these two? It's both 3 million. I'll take that in dollars, cash. Thank you very much. But the one on the right shows us that those 3 zeros are significant. The one on the left shows us that all 6 zeros are significant. So in this instance, if you had this number and you needed to show that some but not all of the zeros were significant, the only way that you can do that is to put it in scientific notation. And that's why we like scientific notation so much. This last number, I don't see a decimal hiding anywhere, so this last number only has 1 significant digit. All right, let's move on. Let's look at these numbers. I'm going to pause the video, and then I want you to write down how many of those are significant. All right, these zeros are placeholders. These numbers are significant. That's 3 significant digits. A better way to have written this would be in scientific notation, 3.14 times 10 to the 1, 2, 3, 4. It's going to be a negative 4 because it's a tiny number, smaller than a value of 1. All right, these zeros in this one are placeholders. Once again, you have 3 significant digits. A better way to write this one down would have been 3.14 times 10 to the negative 1, 2. This next number, they're really trying to trick you now, or I am, because I wrote these numbers down. These 2 are placeholders. This one here is significant because we have a decimal. So when we count the significant digits here, we have 1, 2, 3, 4 significant digits. A better way to write this number would have been 3.140 times 10 to the negative 2. How about the next one? These 2 zeros are placeholders. These 2 are significant because we have a decimal point here. So we have 1, 2, 3, 4, 5 significant digits. Better way to write this would have been 3.140 times 10 to the negative 1, 2. And then these number 5 and 6, they're already written in scientific notation because somebody got a clue that that's a better way to write numbers in science. And here we have, that's a 1 by the way, 3 significant digits. And here we have a decimal rendering this guy significant, so we have 1, 2, 3, 4 significant digits. All right, so if you understand everything we just did, you are then ready to move on to the next video.